right, tomorrow we're going to roll a marble or a steel sphere down a ramp and launch the marble off the table, and your job is to predict where it's going to land by placing a cup somewhere, a certain distance that you've calculated. And the first step to figure out how to do this is to know how fast it's coming off the ramp at the end of the ramp. So here's a little video. And there it goes. All right. Now, for the sake of our calculations, we're going to assume a couple of things. For one, we'll say that the marble is being released, or marble or sphere is being released from rest at the top of the ramp. And two, we're going to assume uniform acceleration, which is going to allow us to use the kinematics equations for uniform acceleration. So let's go to Notability and take a look at how this works. So we've got our ramp here, and we've got a flat section, and there's a vertical distance here, and there we go. So we have pretty much a triangle. All right, triangular shape. It's not. Don't worry about the drawing being perfect. The point is, the marble starts over here at some point and exits the table, and the yellow part is actually a ruler, so you can actually read the measurements. You can release the marble from a very specific location, and then when it exits the ramp, it's at 0, so you can measure exactly how far it's gone. So the equation you're going to use, well, let's draw a picture. Let's draw a picture first. So we've got our ramp. All right, we've got our ball, and we could say V naught equals 0 because the marble's released from rest. Now let's draw a motion diagram showing that the ball is speeding up. Okay, so we're going to assume it's accelerating at a constant rate, and it pretty much is. Not exactly, but pretty darn close. So we want to know what is the speed as it comes off the ramp. Okay, now let's take a look at our kinematics equations. We've got V equals V naught plus AT. We have X equals X naught plus V naught T plus 1/2 AT squared. Okay. And we have V average equals 1/2 V initial plus V final. So the question is, what are we trying to find? We're trying to find final velocity right here. That would be this part of the equation. Okay. Now, final velocity is also here. All right. So there might be more than one way to arrive at this. All right. Initial velocity is 0. So this term goes to 0. All right. Which simplifies the middle expression. Right? If we subtract x naught from each side of the equation, we can simply say delta x displacement is equal to 1/2 AT squared. All right. Now let's use red and green to figure out the top equation if that applies. So if we use red for things we don't know, we do know initial velocity, so we can actually color that one green. We don't know acceleration, so we'll color that one red. And we don't know time, but we can measure it. So because we can measure it, we will color it green, meaning we can collect that information. So the first equation we can't actually solve for V because we don't know A. Okay? But we can get A from the last equation. Let's check it out. So we can measure displacement as it moves down the ramp. That would just simply be, the distance from the point it starts to the point it finishes. We'll call this delta x from there to there, and you can measure that. All right, and we can use a stopwatch to measure the time. So if we know delta x and t, we can solve for a. So first, first step will be to use this equation right here to solve for a. And the second step will be to take a and substitute it into the top equation at the top, and we plug in a and solve for v, final velocity at the ramp. So that'll be our second step. So let's do an example calculation right now. Let's say the distance down the ramp is from v initial to v final. We'll say that this distance is exactly 1 meter. And we'll say the amount of time it takes to go down the ramp is 2 seconds. All right, let's do the calculation. So delta x equals 1/2 at squared. Again, that's assuming that the initial velocity was 0. We're solving for v, okay? So we would substitute 1 meter, 1.00 meters equals 1/2 a 2 seconds squared. Okay, let's do the math here. 2 seconds squared is 4 seconds squared. I'll just show all my steps. 4 seconds squared, right? The 2 gets squared and the s gets squared. So we have 1.00 meters. All right, 1/2 times 4 is 2. So I have 2a seconds squared equals 1.00 meters. And then I would divide each side by 2 seconds squared. 2 seconds squared. And you see the 2's cancel, the s squared cancel, and I'm left with an acceleration value of 0.5 meters per second squared. So I just solved for the acceleration down the ramp. Now I can use that in this formula to figure out how fast it's going at the end of the ramp. So it's a v equals 0 plus 0.5 meters per second squared. That's my a value times t, 2 seconds. And I would get 0.5 times 2 is 1, so I get 1.0, and then one of those s's will cancel, meters per second. So that would be my exit velocity off the ramp.